Hi, and welcome to this tutorial video in which I'm going to show you how to very well understand hypothesis test in theory. The first part of this tutorial will show you the basics foundation of hypothesis test in theory, and the second part of this tutorial will show you how to implement different statistical tests using SPSS, especially student tests on one sample, independent sample, as well as ANOVA test and chi-square tests. So let us first start with the theoretical part of this tutorial, which is the basic foundation of the hypothesis testing.
The general goal of the hypothesis test is to rule out chance sampling error as a plausible explanation for the result from a research study. So in the research study, we can search if whether or not a plausible explanation for the result is just due to sampling. So hypothesis test is a technique to help determine whether a specific action has an effect on the individual in a population. So you make an action, and after the action is made in the population, you try to find out if the action have effect or not through hypothesis testing. So the hypothesis test is used to evaluate the result from the research study in which a sample is selected from a population, first of all, and secondly, an action or a treatment is administered to the sample, and thirdly, after action or a treatment, for example, the individuals in the sample are measured. So hypothesis testing after this measure will help you set a decision on whether or not the action that have been made have an effect or not. So you can see an unknown population before a treatment that have a standard deviation of 20, and the mean of the population is equal to 80. And after treatment we have the same standard deviation, and the mean of the population is calculated. And hypothesis testing will make a decision of whether or not a treatment have an action based on the value of the mean of the population after treatment, based on hypothesis testing principle that we will show you a little bit sooner in this tutorial video. So if the individual in the sample have noticeable difference from the individual in the original population, we have evidence that the action made has an effect. So how to measure this effect using hypothesis testing, statistical hypothesis testing will show you in this tutorial video. How it is also possible that the difference between the sample and the population is simply sampling error. We'll answer this question before the end of this tutorial video. So we can also once more illustrate the unknown original population of mean 80 in our sample, and after administration of the treatment we have also the mean of the population that we will use determine whether or not we can accept that the treatment have an effect on our population, on our sample population. So the purpose of the hypothesis test is to decide between two explanations. First, the difference between the sample and the population can be explained by sampling error. There does not appear to be an action effect. So, thirdly, the difference between the sample and the population is too large to be explained by sampling error. There does appear to be the action effect. So, this illustration show you a distribution of mean of our population, and we in the hypothesis test it will be necessary to to use extreme low probability value if H0 is true. So the distribution of the sample mean is, if the null hypothesis is true, is shown in this graph in front of you. So after computing the extreme low probability values that can be that we call in hypothesis testing a threshold. After computing this extreme low probability value according to the set threshold, we will help we will take the decision using critical region that we will explain to you what it is in this tutorial a little bit sooner. So what is the null hypothesis in hypothesis test? What is alpha level? What is critical region? And the test statistic. So the following four steps outline the process of hypothesis testing and introduce some of the new terminology in hypothesis test that we'll be using in order to set a decision of whether or not to reject or accept the null hypothesis. So the first step in hypothesis test is to set the hypothesis and select an alpha level. The null hypothesis H0 always states that the action or treatment has not effect. So the action or the treatment that we made on our sample has not effect. So they do not change or they do not differentiate the mean of our sample. And according to the null hypothesis, the population means after treatment is the same it was before treatment. So that's what mean null hypothesis. The alpha level establishes the criterion or cutoff for making a decision about the null hypothesis. The alpha level also determines the risk of type 1, the risk of type 1 error. So we'll come back on the risk types in this tutorial video. So taking a normal distribution probability, we can set the different low probability level for the threshold of 5%. 5%, threshold of 0.05. That's the critical value that set the alpha equal 5% level. So that means that when we will compute if on the null hypothesis our variable follow normal law of mean 0 and standard deviation 1, we will reject the null hypothesis when our test statistic will be superior to 1.96. So we'll come back a little bit earlier sooner in this notion. We also have 1% low probability level of 1%, which is 2.58 for the normal distribution of mean 0 and standard deviation 1, and so on. So the step 2 in hypothesis testing is to locate the critical region. The critical region consists of outcomes that are very unlikely to occur if the null hypothesis is true. That is, the critical region of is defined by sample mean that are mostly important to obtain if the action or a treatment has not effect. The phrase almost impossible means that these samples have a probability p that is less than the alpha level. So we have, in the case of normal distribution, a representation of critical region that is the region that is painted in blue. So we have for the normal distribution of mean 0 and standard deviation 1.95% low probability level for a threshold of 0.5%. So middle 95% high probability value if H0 is true. So the probability that the mean of our sample is being equal to 18 is when is equal to the probability that the mean of our sample is superior to 40 after that the standard deviation of our sample is superior to 1.95 is 0.5%. That is the probability that is located in the critical region. So the step 3 is to compute the test statistic. The test statistic forms a ratio comparing the obtained difference between the sample mean and the hypothesized population mean versus the amount of difference we will expect without any treatment or any treatment effect, the standard error. So the last step in the hypothesis test is to that a large value for the test statistic show that the obtained mean difference is more than would be expected if there is no treatment effect. If it is large enough to be in the critical region, we conclude that the difference is significant or that the treatment has a significant effect. In this case, we reject the null hypothesis. If the mean difference is relatively small, then the test statistic will have a low value. In this case, we conclude that the evidence from the sample is not sufficient and the decision is fair to reject the null hypothesis. So we have an illustration of the population, for example, without alcohol, which have mean of 80, normal distribution with standard deviation 4. We have a sample of 16 persons. So we also have a population with alcohol. We have the mean on the normal distribution and the standard deviation of R. The null hypothesis in this case is that the alcohol has not effect. The mean is still 80. We test this hypothesis. What is error in statistic in hypothesis test? So just because the sample mean is different from the original population mean does not necessarily indicate that the treatment has caused a change. You should recall that there usually is some discrepancy between the sample means and the population mean simply as a result of sampling errors. So because the hypothesis test rely on a sample data and because sample data are not completely reliable, there's always the risk that misleading data will cause the hypothesis test to reach a wrong conclusion. So two types of error are possible. Error type 1 Type 1 errors occur when the sample data appear to show the treatment effect when in fact there is none. In this case, the researcher will reject the null hypothesis and falsely conclude that the treatment has an effect. Type 1 error is caused by usually unrepresentative samples. Just by chance, the researchers select an extreme sample with the result that the sample falls into critical region when the treatment has not effect. The hypothesis test is structured so that type 1 error are very unlikely. Specifically, the probability of the type 1 error is equal to the alpha level. So another type of error is type 2 error, which occur when the sample does not appear to have been affected by the treatment when, and in fact, the treatment does have an effect. In this case, the researcher will fail to reject the null hypothesis and falsely conclude that the treatment does not have an effect. The type 2 error are commonly the result of the very small treatment effect. Although the treatment does have an effect, it is not large enough to show up in the research study. So we can illustrate the two types of errors in this table. So we have type 1 error is the probability to reject H0 while H0 where there is not effect. So when which means when H0 is true, and type 2 error is the probability to retain H0 while H0 is false. So in two other cases, we have correct decision. So we also have directional tests. When the research study predict a specific direction for the treatment effect, increase or decrease, it is possible to incorporate the directional prediction into the hypothesis test. The result is called a directional test or a one-tail test. A directional test includes the directional prediction in the statement of the hypothesis and in the location of the critical region. For example, in the original population, if the original population have a mean of mu equal 80 and the treatment is predicted to increase the score, then the null hypothesis will state that after treatment 80 is less than 80, there is no decrease. In this case, the entire critical region will be located in the right-hand tail of the distribution because large value for m will demonstrate that there is an increase and will tend to project the null hypothesis. So a hypothesis test, in hypothesis test, we also have to measure effect size. So what is measuring effect size? A hypothesis test evaluates the critical significance of the result from the research study. That is, the test determine whether or not it is likely that the obtained sample mean occur without any contribution from the treatment effect. The hypothesis test is influenced not only by the size of the treatment effect, but also by the size of the sample. Thus, even a very small effect can be significant if it is observed in a very large sample. Because a significant effect does not necessarily mean a large effect, it is recommended that the hypothesis test be accompanied by the measure of the effect size. We use coherent standard deviation as a standardized measure of effect size, much like z-score. Cohen's standard deviation measures the size of the mean difference in terms of the standard deviation. So we have the two representation distribution of SAT score before treatment, and we also have a distribution after the treatment. We have an increase of 15 in the mean of the sample. So we have also the distribution of the interquartile score before treatment and after the treatment that can be used to measure the size effect of our population. So we also have the power of the hypothesis test. The power of the hypothesis test is defined as the probability that the test will reject the null hypothesis when the treatment does have an effect. So the power of the test depends on the variety of factors during the size of the treatment effect and the size of the sample. So we can illustrate the power of the hypothesis test using our original population with normal with a standard deviation of 40 and the mean of 10. So if H0 is true, H0 equal 40 and standard deviation equal 10, with 8-point treatment effect, we have a mean of 88 and standard deviation which remain 10. The distribution of sample mean for n equal 25 if H0 is true. We have also a distribution of a sample mean for the same 25 with 8-point effect. So in this situation, we have a rejection region of the null hypothesis test. So we will delve now into our practical case to illustrate practically what we have learned in this tutorial video. So we'll take example of Templer and Tomeo in 2002 that reported that the population mean score on the quantitative portion of the graduate record examination general test for students taking the exam between 1994 and 1997 was 558 with standard deviation of 139. Suppose we select a sample of 100 participants we record sample mean equal to 585. So we compute one independent sample test for whether or not we will return a null hypothesis m equal 558 at 5% of significance level. So the step one, as we show you earlier, is that we need to state the hypothesis. So the population mean is 555, and we are testing whether or not the hypothesis the hypothesis is equal or is not equal or correct. H0 is so m equal 555, mean test score are equal to 552 in the population. H1, which is the alternative hypothesis, is that mean is different to 558, means test score are not equal to 558 in the population. So in the step 2, we set the criteria for the decision. The level of significance is 5%, which make the alpha level of 5%. To locate the probability of obtaining the sample mean from a given population, we use the standard normal distribution. We locate the z-score of the standard normal distribution that are the cutoff or critical value for sample mean value with less than 5% probability of occurrence if the value stayed in the null. M equal 558 is true. So in the step 3, we compute the test statistic. So we can notice that step 2 set the state for making a decision because the criterion is set. The probability is less than 5% that we will obtain a sample mean that is the least, that is at least 1.96 standard deviation above or below the value of the population mean stated in the null hypothesis. In this step, we will compute the test statistic to determine whether the sample mean we selected is beyond or within the critical value we state in step 2. The Z statistic formula is the sample mean minus the population mean stated in the null hypothesis divided by the standard error of the mean. So we write the formula mean minus mean of the population under the null hypothesis divided by the standard deviation of the population, which the standard deviation is given by the of the sample is given by the standard deviation of the population divided by the square root of the sample. So our calculated standard deviation is 13.9. So the z-score is, as we said, the mean minus the population mean stated in the null hypothesis divided by the standard error in the mean of the mean. So we find out that the test statistic is 1.94. But what we in the last step of the test, we need to make a decision. To make a decision, we compare the obtained value of the critical value We reject the null hypothesis if the obtained value exceeds the critical region. Figures show that the obtained value is 1.94 is less than the critical values, which is set as at 1.96. It does not fall into rejection region. So the decision is to obtain the null, to return the null hypothesis, which means that the obtained value of 1.94, which failed to reach the cutoff for the rejection region, so we return the null hypothesis, which means that in our sample population, the mean does not increase or does not change in our sample.
Using SPSS, we focus mainly on different student tests, especially tests that allows you to compare mean. So that's one sample student test, independent sample student test, as well as one-way ANOVA, in order to show you how to take some decision in practice. So we'll very focus on interpretation. We'll also show you how to make a chi-square test using cross-table in SPSS. So let us start with student tests and their interpretation. One sample student test is a test in which we have one variable in which we are going to test for if whether or not the mean of the sample is equal to a certain value. So, for example, in this database, we have many information, including the age of the patient in our database, and we are going to test for if whether or not the mean is equal to a certain value, for example, 30. So to make one sample student test in SPSS, just go on analyze. When you are on analyze, go on compare mean, and there are many options here, and just choose one sample student t-test. So you click on one sample t-test. The first step is to select the variable that you are going to test. Highlight this variable and use this arrow to put it into test variable section. So while you have put your variable in variable test variable section, you should choose the value of the mean that you are going to test for. So here I'm going to test if whether or not mean of my sample is equal to 30 years old. So as I have put here in the test value, the value 13, I can just click on OK, so that result of my test here. So age, we have many information in our variable age, which is 443 person in the sample. We have the mean, which is mean of 35.22. We have the standard deviation. So a very interesting table that we are going to use in order to analyze and find the conclusion of this test is the second table here, which gives the t statistic of negative 15.62. The degree of freedom is 442, and here is the p-value in the third column of our table. Of the fourth column of our table, we have is a p-value which is 0.000. Our p-value is less than 5%. means that we should reject the null hypothesis, which was set as which say that the mean of our sample is equal to 30-year-old. So we cannot accept the fact that our mean of our sample is 30-year-old. So let us redo our test and choose for a test value just to 25. So you have seen that the mean of our sample was close to 25-year-old. So we click on OK, and that in this second analysis, you can notice that our p-value is just equal to 0.459, which is significantly more than 5%, which means that we can just, in this case, accept the null hypothesis, which say that the mean is equal to 25. So in this case, we have to accept the null hypothesis. Sample student test is conceived in order to evaluate the difference in mean between two groups, two independent groups. So we have a variable in which, for example, the age. We are going to see whether or not there are two groups have different mean in age. So for this tutorial, we'll just take an example of body mass index. So we have a database on body mass index recorded on student in secondary educations, both male and female. So we're going to see in this tutorial whether or not the body mass index differ from girl to boy. So we have our variable, the body mass index. So to run independent student test, we just need to go on analyze and compare mean. So you go on independent student test. So you click on independent student test, you select the variable to test. So our variable that we are going to test here is BMI. BMI is body mass index. So we use the arrow to put it in the test variable section. So the second step is to select the grouping variable. So here our grouping variable is student gender. We are going to see whether or not there is a significant difference between body mass index among males and females in our sample. So we highlight the student gender variable and put it in grouping variable. So the third step is to define groups. So we have seen in our group that we have two modalities for student variable. For student gender variable, which is one for female and two for male. So we will click on the define group button here. So we enter 1 for group 1 and 2 for group 2. So then we click on continue, and after that we click on OK, and the output will be printed here on your screen. So we have in the first table the group statistics. So we have numbers of observation. We have 1,425 female students and
867 male students. So the mean among the group in the group of male student is 21.34, and in the male population we have 19.74. So we have a standard deviation of in each group as well as standard error mean. So the second table here give information in independent sample test. So what is really interesting here is a value of the student test, which is here, and the degree of freedoms. We have also the significance of the test. So the very important value here is a significance of the tail of the two-tailed test. So we have a p-value, the significant, which is the p-value here, is equal to 0.000, which means that you can just reject the null hypothesis, which is the equality of mean between women and female. So we can not accept the null hypothesis, meaning that mean body mass index is different between female and male population. And we come back in our group statistic table, we can see that body mass index is more than among female is more than the one among male students. So we can just think that female students have much higher body mass index than male. ANOVA test is a statistical test mainly designed to search for mean difference between groups. So the aim of the ANOVA, one-way ANOVA test is to search is whether or not the mean is different, mean of the quantitative variable differ between groups. So in this tutorial case, we have two different variables. We have salaries and we have different categories. So we have agriculture, we have industry, and we have sales. So these three sectors in which we are going to see if whether or not the mean salary the salary differ between these or can be considered to be equal in these three groups. So to run ANOVA test in SPSS, you just need to go in analyze, compare mean, and choose the last option of the test, which is one-way ANOVA. Then click on one-way ANOVA. So the first step is to select the dependent variable, which is the quantitative variable, to put through this arrow in the dependent list. So the second step is to select the category factors, which is category that use this arrow put in the space related to factors. So we can go in option, choose to have descriptive statistics, fixed and random effects. So we will not select this option because 99% of tests are based on fixed and random effect models. So we select homogeneity or variance to see if whether or not the variance is variance differ between different groups. We also have Brown, Forsyth, and Welsh. So you can also plot the mean plot. You can also do a mean plot. Select the mean plot and then click on continue and then click on OK. So we can the first table that appear in our estimation result is the descriptive statistics. So we have here the salaries, and the first the very most important piece of information in this table are the mean and standard deviation of our variable. We have mean in agriculture, we have mean salary in industry, and as well as services in standard deviation of variable between different groups. So the test of homogeneity of variance is the test that search for the difference, if whether or not the variance are homogeneous between different groups. So the most important value to interpret in this test of homogeneity of variance is the p-value, which is noted here 6. So the p-value here is equal to 0.000, meaning that can consider that variance are not statistically equal. So variance are different among different groups, agricultural industry or services. So this 3.39 standard deviation in the service group are statistically different to the other standard deviation of in different other groups. So the third table that we have in this result is the ANOVA test, which is the test which give the result about the difference between groups, between means. So we have the number of Fisher statistic here in the last but one column. So the Fisher statistic is 3.73, and the p-value is 0.02, which is less than 5%, meaning that we reject the null hypothesis that mean are equal between different groups. So we cannot accept the fact that mean salary is equal among groups. So in agriculture, industry, and service, the mean considered is statistically different to the mean calculated in the other sector. So we also have robust tests of equality of mean. So we have Welsh and Brown for sites. So we have different degree of freedom as well as p-value that are less than 5% as previously. And in the plot, in the mean plot, we have the different value of the plot of the mean of mean salary. So this plot can materialize the difference between the mean salary in different chi-square test is a test which is used when you are going to analyze the relationship between two qualitative variables. Instead, when we have quantitative variable, we usually use correlation in order to analyze whether or not there is a link between two variables. But in the case of qualitative variable, we may need to use a chi-square test in order to analyze the relationship between two variables. So run chi-square independence test. Just go on analyze. Let us just notice that is the database on a survey on a company client. You have the gender, you have age category, you have reason of purchasing a specific good, you have payment method, you have the distance between the house of the client and the company where the good is being purchased. so or not. So we're going to analyze the relationship, the dependence of of some of variable in our database. So to run chi-square test, just go and analyze descriptive statistic, cross descriptive statistic. Click on cross table. So when you have clicked on cross table, you have this interface that appear. So you can select a row and column variable in order to analyze correlation, the link or the dependence or independence between variables. So don't mind if you invert. So if you put in a variable in row or column, so it doesn't matter what when you put variable in row or column. So for example, to analyze the whether or not gender and age category are dependent or independent variables, select for example gender and put it on rows, and after that you select age category and put it on column section. So to perform chi-square test, you go on statistic and select chi-square. So then you click on continue and then you click on OK. So when you click on OK, you have this table results. So you have case processing summary that give percentage of valid variable. So all variables were put in the analysis, which means that they were not missing variable among gender and age categories. So we have a cross tabulation between gender category and age category. In each cell's concern, we have the count of the cell. So, for example, men which were aged between 18 to 24 were 16, and men aged more than 64 were just 6 in our sample. So we have in the last table chi-square test. So the first line is chi-square. In the second column we have 6.187 chi-square statistic test with 4 degrees of freedom, and the asymptotic significance here is a p-value which is 18.6%, which means that we can just accept the null hypothesis, which is gender and age category are independent variables. So we accept the null hypothesis, which means that the two variables are completely independent. So we cannot use for the age category, for example, in order to predetermine the gender of a client. So let us look at other variable. We go on descriptive statistic. We choose analyze descriptive statistic cross table. So we remove, for example, age category and choose the reason of payment. So we choose reason of payment. We have already selected chi-square. Continue and then click on OK. So you see that in this case we have a asymptotic significance which is 9.5%, which means that if we consider a 10% level, we can just reject the null hypothesis, which is the independence between the gender and the reason. So we cannot reject we cannot accept the independence between gender and reason. So the reason of payment can predetermine the gender of of a client. It can mean that there are some reason which are more used by some gender categories. Uh, so that can be the explanation of the result of this that if you consider a 10% level. Let's look at second reason variable, reason 1, reason 2. So you can see that reason 2 are highly significant, which mean that so the reason are price, commodity, service, and others. So can we have a asymptotic significance which is significant even at 1% level, which means that we cannot accept the null hypothesis. We reject the null hypothesis on of independence. It means that there are a dependent relation between the reason of and the gender. So there are probably some reasons that are more present in some group categories. So to make a little bit deeper in the interpretation, you can, for example, use old ratio in order to analyze whether or not price influence positively on or negatively in the gender. So that's it for this chi-square test, and hope we help you understand the chi-square test and the notion of independence between qualitative variables.